Greetings. In the first part of this problem, I solved for you all the different properties of the test section where it was nominated station 1. It was denoted as station 1. Now, what I want to do is to move back to the truth and see what the truth properties are. Now, at the throat, which we call it the first throat, the knowledge that we have about the first throat is that T0 equals 300 Kelvin. It is the same as all points throughout the wind tunnel from the entrance, and P0 is 100 kilopascal because the flow has been isentropic from the entrance, and therefore total pressure has not changed. Total stagnation pressure, they are both the same thing. Now, what we do is that when we were talking about the test section, we learned that A to A star is 1.4390. I mean, we learned the ratio between this test section, the area of this section, and also the area of the throat. So we should return from the test section to the throat and calculate the throat diameter. A over A star, A1 over A star was 1.4390, and now we can move to our table and see what different properties at m equals 1 are at the throat. You see, at the throat, which is this in this table is this line, okay, Mach number is 1. A to A star is, of course, 1 because A area is the throat area, so A is 1. Two properties are important for us. P over P0 is 0.5283, and T over T0 is 0.833. So these are the values at the throat. Well, A over A star is 1.4390. This means that this area should be the throat that produces Mach number 1.8 at the test section. And now what we could do is to calculate this in terms of diameters. You see, we could write it P d1 squared over 4 divided by P d star squared over 4, which are the two areas, equals 1.4390, and therefore the two p's and the two 4's cancel out. We learn that d1 squared over d star squared equals 1.4390, and since d1 is 0.25, we conclude that v star would be 0.2084 meters, and that is meters as well. So now we know what the throat diameter, the minimum diameter, the throat diameter, where Mach number equals 1 would be. We know the value for the diameter of the throat. We continue with calculating a number of other properties at the throat. P star equals 100 times P0 times this value times 0.5283, and that would be 52.83 kilopascal. T star, the temperature at the throat, static temperature at the throat, would be 300 times 0.8333, and that would be 250 Kelvin. And with the knowledge of T star, just like before, we calculate A star, the speed of sound, which is square root of gamma r T star, and that equals 1.4 times 287 and times 250, and A star would be 316.94 meters per second. Also, since it is sonic velocity at the throat, V star and A star are equal, and therefore V star would also be 316.94 meters per second. Now, these are all the values for one star. Here, we could show them on the table as we did before. You see, this is our table, and the star values that we calculated for the throat, we could show them here. You see that the pressure is 52.83 kilopascals. The temperature is 1250 Kelvin. The diameter is 0.2084. Mach number is, of course, 1. Speed of sound and the speed of the flow are the same, and both equal 1. Mass flow rate would be the same at the throat as it was at point 1, and uh, that's throughout this tunnel. Mass flow rate would be the same. That's what the mass uh, mass conservation equation tells us. We will also show all these values on the TS diagram, and it will be very informative. You see, the flow started at this point, the stagnation conditions continued through an isentropic path, and at some stage, like say here, the flow reached 250 Kelvin. This is the T star. T star equals 250 Kelvin. T0 is this one. So this is the path it followed. At this point, T star is 250 Kelvin, but the P star equals 52.83 kilopascal. So we have both P star and T star on this diagram. There is one important uh, uh, thing that you could show on this diagram, and that is that this range is subsonic. The flow up to here is subsonic. This is sonic flow, and after that, this range is supersonic. And this is supersonic flow. So there are two different ranges of flow that we have. The flow speeds up from 0 to Mach number 1, goes through all the subsonic range, and that happens from here up to the throat, and then it continues to supersonic values up to here, where is station 1. The static temperature would be 182.04, and the pressure reduces to 17.40. And at this station, where there's star values here, m equals 1. You see, it's a very, very important point if you gain the capability to translate all these physical descriptions to these equations that I have shown you here, you see, to these equations, and also interpret all of them this diagram. So if you can do that, then you're very good at thermodynamics. You see, learn about the physical descriptions, connect them to the equations, and also show them on a diagram. If you could do these three in every problem, then you're in a very good position and you have learned thermodynamics very well. Now, there's one further discussion we need to make, and this very important point. The point is that if air is humid at entrance, which of course generally air is humid, um, and the humidity might be 10% or there might be 70 or 80%. What happens to the water in the air as it goes through the tunnel? You see, we learned that the pressure here drops to 17 kilopascals, and the temperature drops to 182 kelvins. 182 kelvins is almost 90 degrees, minus 90 degrees centigrade. So what we expect is that not only the humidity in the air would condense, also it would freeze. You should see ice cubes in the tunnel. But let's show it with numbers. It's very important to show it with numbers. And to start the point, let's assume that the flow that enters this tunnel has a relative humidity of V equals 10%. So it's not that humid. It's in fact fairly dry air, fairly dry, unpleasant air. If it's more humid, then uh, the worse our problem would be. Now, uh, we know that V equals PV over PG, and for the temperature of 300 Kelvin at entrance, T equals 300 Kelvin, and therefore PG equals 3.5369 kilopascal. That's the saturation pressure for this temperature. Now, how much water would be in the air per kilograms of dry air? W at point 0, and for this 0, I mean at stagnation conditions where velocity is 0 and the entry flow would be 0.622 times 0.1, 10% humidity, times 3.5369, and divided by 100 minus 0.1 times 3.5369. And the outcome for W, the specific humidity, would be 0.00221 kilograms of vapor per kilograms of dry air. Now, the minimum temperature that I found in the tables, um, just to read the saturation conditions, was 200 kelvins, and what we have at station 1 is 182. But let's see what happens for 200 kelvins. At 200 kelvins, T equals 200 Kelvin. Psat, saturation pressure, is 0.00016 kilopascal. Okay, now at this condition, what would our content mean? You see, W would remain the same for 0 or 1. If W1 equals W0, I say if W1 equals W0, what sort of humidity we would have? That equals 0.00221, and that would be 0.622 times Phi at point 1, which we don't know it. If the number that we calculate is more than 100%, that means more than 1, it means that we would have uh, condensing water vapor, and water vapor would condense. 3 times 0.000162 and divided by 17.40 minus V1 times 0.0000162. And the outcome for V1 would be 379.89. You see, if it was 1, that means that it is saturated air. If it is 379, it means that there is loads of water in it. And that is really the case. I mean, for those who have seen a wind tunnel like this, that it draws just normal air from the ambient into it and speeds it up to speeds as high as 1.8. It's just exactly that you have opened the tap water into the wind tunnel and there's loads of water flowing in the air. I mean, it is tap water flowing into the air. The condensation is so high. And therefore, there must be some means of drying the air, either with different mechanisms. You could produce dry air and then introduce dry air into the wind tunnel. Otherwise, the single phase air flow into the tunnel, and the text section will just be meaningless. Well, in the next section, I will continue this problem for a normal shock wave in the test section. Thanks for watching and see you in the next video. Cheers.